So we are going to continue our discussion of fifth postulate module that we are going to see how there have been attempts historically in the history of non-Euclidean geometry to attempt to prove the dependence or independence of Euclidean of fifth postulate on Euclidean geometry. So there have been attempts to prove the fifth postulate can be seen as a system which can be derived from other four postulates which have been which have been proved. The attempts have been some sort of failures, or there have been shown that the existence of Euclidean fifth postulate is independent of the other postulates. So if you see, for example, if you just in the Greek antiquity, the person of the name of Proclus, who was in the time of Ptolemy. So he doesn't reproduce a proof, but there is a sort of argumentation which he has gained in that context, in the context of fifth postulate. So which essentially hinges on the fact that if the interior angles of the on the one side of two of the parallel line, two parallel lines which is cut by a straight line, the interior angles on the one side is of the sum of interior angles of the two sides is of interior angles is greater than 180 degree. It should be the same in other side also. For example, if there's two parallel lines and sum of the interior angles may be greater than 180. So if you have two parallel lines, they are cut by two parallel lines. So if we assume that the interior angles on this side are 180 degree, greater than 180 degree, so interior angles on the other side is also greater than 180 degree. So this will lead to a simple contradiction that in a quadrilateral, the sum of four angles of a quadrilateral is four right angles or 360 degrees. So it will come more than that. So this is a contradiction. So this is one way of arguing the same thing. So one is the attempt of this is Proclus. So other proof of this Proclus is that if there is a parallel line, this is a parallel line A and B, and there's another parallel line C and B, and E, and if you assume that these two parallel lines are cut by another straight line, so what does it mean? So cut by a straight line, maybe B, and if you extend it, so if you see, if you extend it, if this parallel line is if one of the lines intersects this line, it should also intersect this line also. If it doesn't intersect this line, so this will assume that it doesn't intersect this line. So you can extend this parallel line this way. So you can make it this, you can make it this, you can make it this. So a point will come, this the line which is going to assume it's going to cut. If you can make the angle slanter and slanter, there will come a stage, the parallel line, which is the line which is going to cut these two parallel lines. If it is not the shortest distance of a triangle like this, if it's a straight line, so it cuts it into two. So if it's not, if it doesn't cut into the straight line is the shortest distance, perpendicular distance, which cuts the two parallel lines. So if it is not the shortest distance, so there is a possibility of increasing the length of this parallel line, which is going to cut it. We can do it. We can reach a stage that this parallel line, this line, which is going to cut these two parallel lines, it will be such that it will somehow meet one of the parallel lines at some infinity or some point. But we are assuming already that these line, a straight line extends up to infinity. So this means that this will lead to contradiction. So this if it cuts this line, it will cut also this line, and the length of this line which is going to cut this line, it is always going to be shorter than the distance between it's always going to be shorter than one of the parallel lines. So it's a argumentation which is being conjured, or it is being not conjured, it's put forth by Proclus. So the fallacy lies in the assumption that parallels are equal distant at any rate, that parallels are so related upon being produced indefinitely. The perpendicular from a point on one to the other remains of finite length. So this should remain of finite length. If it's not finite, so we can it will lead to. So this implies that the former implies that fifth postulate has been already proved. Later also, as we will see later. So there can be arguments the other way around also. So it can be a proof, or it can open the can in the other direction, that really you can construct a parallel line which will meet at infinity. So you can say this proof is an argument in favor of fifth postulate, the validity or veracity of fifth postulate, but the argument can be constructed in the other way around also, logically. Now this is Proclus. The other argument has been given by Nasiruddin Mullah Sadra. He's also not Nasiruddin Tusi. He is called a Persian mathematician of Iranian descent. So he has been, you can say, he was Euclid of Persia, or whatever. His maybe time has been 1201 to 1274. So he has there are detailed arguments how he has constructed the proofs of the fifth postulate. So this book has not dealt that those arguments in length, but some of the gist of the arguments have been reported here. For example, what the arguments of, for example, fifth postulate is, for example, so if you assume, so if we just somehow summarize two sort of arguments, if you assume that there are two lines, A and B, C and D, there are two assumed lines, and there is a parallel line E. So you can, from this line, we are going to draw a perpendiculars on this line. So you draw from E, there is a perpendicular, you draw F. From G, you draw H. From I, you draw G. So this is the figure. So, but you can say that the perpendiculars drawn from this point, though they may be perpendicular on this line, but the angles from which they can be made from this point, they may not be necessarily perpendicular, because this line is having some slant. So it will have slant in a direction. So it will. So if you have it will have slant in the direction such that the angles which will correspond to in that direction, this direction, they may have acute angles. And if you want to measure them in this direction, they may be obtuse angles. They may be acute and obtuse angles in vice versa directions. They are unequal angles. So if you want to extend the line this side continuously, so it will lead to some acute angles, and if you want to extend this thing, the angle will grow in terms of obtuseness. That's it. And concurrent to this figure, you can say that if we assume that it's a famous figure, if you assume that there are if you assume that we have at the extremities of a line segment A and B, so we draw perpendiculars like AD and BC, and you can join, then if you join CD and if you join DB, that's fine. So if you want to prove that CDA and CDA and this CDA on this angle, CDA and DCB and DCB, sorry, see, or right angles, that's known. This angle and this angle is right angle, so you can say this angle is right angular to this angle. We have taken a line segment AB, and we have made two perpendiculars, A to D, B to C. And now you join the segments, so this is perpendicular to this and this is perpendicular to this. So from this, now there's an argument. So you have argument of reductio absurdum. So you reduce some arguments to the point that if you are going to reduce the arguments in such a way that at the end you will just come to realize the absurdity of that thing, and you leave it leave the original assumption. You cannot either prove original assumption or you have to revisit that assumption. So using so we assume that if the angles DCB were acute, if this will acute, so DA will be shorter. So DA will be shorter. So if you assume that this will acute, so you can have this sort of motion. So if you assume that it will not be a right angle or it will be acute angle, so you can say that somehow this thing will just if the distance will become shorter, you can infer from this, contrary to the fact. So hence angle hence the angle DCB, hence the angle DCB is not acute. So if you assume that this is not a right angle, if it is acute, so this will be shorter, and from this you can say it will not be contrary to the fact. So neither it's acute. If you assume it's obtuse, then it will be the line will be greater. You can see from this, it will just not shorten. Its length will increase. So in both cases, whether it's acute or whether it's obtuse, it will not. It will change our this thing. So this means that all the four angles of the quadrilateral are all four. So it's sort of angles of the quadrilateral or 90 degrees or the total sum. So it's also sort of argument which I previously said in that continuation, that if two parallel lines are cut by two parallel lines, if the sum of interior angles is more or less than 180 degree, it will lead to some sort of a contradiction. So maybe to go to proofs, maybe these are just pictorial, what I should say, mnemonics to just see how he generated the arguments. So you can just go and see yourself to just further continue how we can just did elaborate thing. Then the next comes in this series Wallis. So Wallis maybe so according to the books he has further the arguments of this 2C. So maybe his reimagining this thing. So what the arguments which are given by that he also now what he has done is again the argument seems to be like this. So if you take a parallel line and if you assume you assume this one line, you assume one line, this is CD, this is AB, this is AB. Now there's a line which is which cuts both of these two lines, both of these two lines. So this is A, B, C, D. So this is H, this is F. Now what we are going to do is we are going to just extend a line like J, L, K. This is G, I, this is E, this is F. So what if you assume that given lines A, B, and C, given lines A, B, and C, D, given lines A, B, and C, D, cut by traversal. So A, B, and C, D are cut by this E, F. So if they are cut by E, F in the points G and H respectively, then the sum of angles BGH and BGH are less than 2 right angles. So the sum of these two angles BGH and BHG, this. So this angle and this angle. So since they are, so sum of this angle BGH plus DHG are less than 2 right angles or less than 180 degree. If you assume that. It is to be proved if AB and CD will sufficiently. So if we are going to sufficiently meet, if we are going to sufficiently extend these two lines, they are going to just cut each other at some finite distance, or if you extend them, they are going to meet at some point in remote future, or maybe infinity. So it's easy to show, for example, it has to be proved that AB and C will sufficient. So it is easy to show that angle EGB is greater than angle GHD. Now what we are going to show? The angle, it is easy to show that angle EGB, this angle is greater than GHD. GHD. So GHD. So this angle is also greater than this angle. So if it's greater than this angle, so if the second HT is moved along EF. So if it is moved, G is moved along EF is this. So if it's moved along EF, so HD is usually attached to it until H coincides with the initial position G. That's fine. HD takes a position GI. So if you take this H from H, you take a position I. This is GI. Lying entirely on GB. Lying entirely on GB. So you see, so you can take a line from this GI. So it's line on GB. can construct a line GI, line entirely above. So you can construct a line GI which is lying above this GB. So in the similar way, if you assume that it's moving, so if it's moving, if it had been earlier here, now it's here. So you can say you can construct a line GI which may be parallel to this line. So when it coincides with JK, cutting GB at L. Now, if you assume parallelly, if it was a parallel here, so now it has moved down. So there, the same parallel line here, it's going to cut this JK at the point L. So it's going to cut JK at the point L. That's fine. Now, if one constructs a triangle on the base of GH similar to the triangle GJL, we construct a triangle construct on the base of GH. On the base of GH, we construct a triangle similar to GJL. So GJL. So if it's a triangle, so we can construct a triangle. So if it's a triangle, this is a triangle. So we construct. So we can construct. This is one triangle. So if it goes again down, we can construct another triangle. We can construct another triangle. So we can take this triangle. So from this, this straight line was like this. So it was like this initially. Then we had some motion here. Again, we had some motion here. So we are going to change this thing. So this triangle will, if it cuts here, later stage it will just cut here. Later stage it will cut some a distance lower to it. So at some point we can say HD cuts GB. So HD is going to cut GB. So this triangle, the length of this triangle is going to just increase. So at some point in time, this is going to cut this line is going to cut this. So from this, what do we arrive at? We arrived at what? The given a triangle, it's possible to construct another triangle similar to it of any side. Then this essentially follows. So if you can construct a given triangle from these two lines, so it's always possible to construct a triangle of any other size. For example, once this line is going to just drop slow, you can construct triangles of similar size that the two lines should intersect from this augmentation. So if two angles of the lines which are less than 180 degree or so, they are going to meet. But the argument is that we have constructed from these two parallel lines. So from these two parallel lines, we constructed triangles, and from those triangles, we constructed triangles of different degree. And from those triangles, one of the lines of those triangles, it's going to just cut this point. So this is an augmentation which is there. Now there is another person of the name of Setye Rai. So maybe he tried to find a flaw in the, again using this argumentation of reductio absurdum, trying to show things, trying to prove things till in a certain way, till we just assuming certain things, till just show that those assuming will lead to some absurdities, and we have to revisit that thing. And in that, we have to be logically demonstrative to that. So what he is again going to say So using Sakurai is basically so if you again take the argumentation of, for example, 2C of devising a quadrilateral of sides AD and BC, and two quadrilaterals having perpendiculars. So if you assume that the angles are not interior angles are not greater than 180 degree or less than 180 degree, they should lead to some contradictions. So what are the contradictions? So I'm going to, so if you only state them, the statement is that if taking the quadrilateral argument that uh, quadrilateral argument is that if one of the hypotheses is true for a single quadrilateral of the type under it is true for, if it is true for one quadrilateral, so if you assume, if you just somehow change this thing, that some of the angles of the quadrilateral which are formed by parallel lines cutting two parallel lines, they can be greater than or less than two right angles, then if it's true for one quadrilateral, it can be true for any quadrilateral. So on the hypothesis of the right angle, the obtuse angle or the acute angle, the sum of angles of triangles is always greater than or equal to. So if it's extended to quadrilateral, it can extend it, the argument can be extended for triangles also. That if it's true that we can construct a quadrilateral whose sum is greater than two right angles, four right angles. So it can be true for any other quadrilateral. This argument can be similarly constructed for triangles. If the sum of three angles of triangles is greater or less than 180 degree, it can be true for any other triangle. So, and the third one is if it exists for similar triangle for which the sum of angles is greater or equal to 2 right, then it follows the hypothesis of 2. And the third and the fourth is two straight lines lying on the same plane, either in on the hypothesis. This one is important. So two straight lines lying on the same plane have either in the hypothesis a common perpendicular. So if two lines, they are straight lines, either they have a common perpendicular, or if producing the same direction, either meet at one another at a finite distance or continuously approach each other. So you can have some germs of fifth possibility. If there are if there's a perpendicular which is cutting these two lines, either they will never meet, or if you extend them, if it's not a perpendicular, either they will meet at some finite point, or they are going to forever meet at some point in infinity or whatever. Either meet one another at a finite distance or else continuously approach one another, or continuously they are going to approach one another. So what he says that Sakurai namely, the hypothesis is there that when produced to infinity merge into one straight line and have a common perpendicular at infinity. So if there is a possibility of these two lines merging at one single line, or having a common perpendicular at infinity. So these are indirect inferences or conclusions which have been constructed. Now there is another person of the name of Lambert. So he used to construct these parallel postulates from the arguments of spherical trigonometry. Maybe in medieval times, maybe there were problems regarding whether the Earth was round or not, and there have been various Arab mathematicians who just went into this discovery of spherical trigonometry. Maybe out of those developments, they had an indirect influence on how people constructed spherical geometry. And in that context, the area of triangle, the argument was the area of triangle is proportional to spherical axis. So this is the thing, that area of triangle, if you construct a triangle on a sphere, so the area of triangle will not remain 180 degree. It will be there will be some spherical access to it, less or more, whatever that is. It depends how we construct. So these are the arguments, and at the end we are going to there is an argument of maybe there is an argument given by Legendre, or construction given by Legendre, which assumes things towards that thing. The argument, Legendre's argument. So what's the Legendre's argument? The sum of angles of sum of three angles. So I'll write three angles of triangle cannot be greater than two right angles. So they cannot be two right angles. A, B, C, D. So if you construct a triangle, such that so the sum of angles of the triangle cannot be greater than, or so if it's if it is so there's an indirect to it. So this is an indirect argument. So what we assume, that if the sum of three angles of the triangle cannot be greater than two right angles, so it is based on a premise that you can prove this thing only if you assume that the line is a straight line. There's an unconscious. But even if you prove this, if you are going to prove this, that some of the three angles of the triangles cannot be greater than two right angles, you are proving this statement. But the premise of the proof is that we unconsciously assume that the line is a straight line is infinite. But the assumption, the proof cannot be held valid, because this proof, which we are going to prove, assuming that some of the angles of the triangle are greater than 180 degree, it proves that you cannot prove it, but in the process you prove that the line on which this assumption is, it's not infinite. So this is the way you can have it. We can just show that this something is there. So you have to do more to it to show the fifth postulate is there. So what we are going to do, assuming that sum of the angles of the triangle ABC is 180 degree plus alpha, that angle CAB is not greater than the others. So that's it. So we are going to construct a triangle, join A. So we are going to construct a triangle A to D, and its midpoint of this and this. So I'll just write it like this. So we are going to have this is midpoint of this and this. This is this midpoint of this and this. Join A to B at the midpoint of BC and produce AD to E. 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 So that D is equivalent to AD. So that DE, this is equivalent to. So this is equivalent to this, and this is equivalent to this. And from this, you can also show that these two. So you can show that these two triangles can be congruent triangles. This is equivalent to this. This is equivalent to this. So this triangle is congruent to this triangle because this angle is equivalent to this. You can show it this way. So if their triangles are congruent, triangles BDA, triangle BDA is congruent to triangle CDE. So if it is that way that are congruent, it was easy that the sum of angles of the triangle AEC equal to the sum of triangle. So if you assume that, this means the sum of triangles, angles of the triangle ABC. So ABC sum of the triangles AEC, sum of the triangles AEC, sorry, I'll write it again. Sum of triangles, sum of angles of triangle AEC is equal to sum of angles of the triangle is equal to sum of angles of the triangle on ABC. AEC is equal to ABC, angles of the triangle ABC, namely 180 degree plus alpha, and that one of the angles CAE and CAE, one of the angles CAE, one of the angles CAE one of the angles CAE and CAA, CAE and this angle and this angle CAE, this angle and this angle are equal to or less than 1/2 of the angle CAB. So they are. So this angle is equal to this, or it is half of this angle, this entire CAB. So you can say this angle is equivalent to this angle, or this angle is equivalent to this angle, or it is half of this angle. You can just show it this way. So by applying the same, the triangle AEC, one of the angles is equal to less than. So you can, if you have this argument, you can, if it's for this line. So again, if you have used this argument for this triangle, we have cut it. So you can again make another triangle and taking a line from this point and again halve this angle and make corresponding again another triangle which is going to meet it at other point, and you can just successively make angles smaller and smaller such that, for example, and with the angle sum equivalent to third angle with the angle sum, third angle with the angle sum is 180 degree plus alpha, and one of the angles is less than, if it's less than one of the two square, or in one of the two square CAB. So you can make this angle smaller and smaller. If it's midpoint, you can again construct a midpoint, and you can construct that this triangle continuously. And by postulate of Archimedes, again, the way we in the previous class used a postulate of Archimedes, here we are also going to use postulate of Archimedes, such that, or if we increase, so 1 by 2 to the power n is always less than CAB. So you can make smaller angles, which is less than this angle. You can make smaller and smaller, 1 by 2, 1 by 2 square, 1 by 2 cube, so on and so forth, such that angle CAB can be made less than K alpha. Can be made. Angle CAB can be made less than K alpha, and K is less than 2 to the power n. And from this argumentation, 1 by 2 to the power n is less than CAB is less than n. Less than alpha. So at the end, from this argumentation, if it's not clear, let you think over it. That the sum of angles of the triangle last obtained is greater than two right angles. So which is not possible. So it's absurdity we have got. So from this argumentation, that if you assume sum of angles, if you assume sum of DA is equal to sum of the angles AEC, is equivalent to ABC, and ABC is equivalent to ABC is equivalent to 180 degree. The total angles, sum of angles is greater than 180 degree. So the proof is similar to that of proof given by Euclid in his book, what I should say. So maybe this is called, by Gauss says this proof is the reef on the wreckage. This proof, although it needs a bit of more involvement to just ponder over it and see it. How the argumentation goes and the construction goes in that thing. So there are a couple of other proofs which are there in the book, but I just only quote one, I'll read one of the statements and then stop. For example, if there exists a single triangle with sum of angles less than two right angles, the sum of angles of every triangle will be less than two right angles. So the argument, there are other proofs also, so they have a similarity to it, and the construction to it may be different, but the argument is like the same, that we can construct angles in a triangle greater than 180 degree or less than 180 degree. We can construct similar triangles everywhere else. So in the next class, we are going to continue with these other attempts towards these things. Thanks.